welcome back. We are talking about section 5.3, the definite integral, and the fundamental theorem of calculus. We have tackled most of our learning objectives in previous videos. Today we're going to try to work on using the fundamental theorem of calculus to solve applied problems involving net change. And there's technically one other thing we're going to do first as well, just kind of a conceptual deal, but let's get ourselves set up. So the first thing is just one of these, like monster definitions slash theorem things that are just kind of hard to piece together without an example. So we're going to try to move to an example, but I'll say at least that the majority of these things, the constant multiple rule, the sum rule, the difference rule, basically all kind of have the same strategies associated with them that the indefinite integral does, like when you're doing anti-differentiation and you can break stuff up over pluses and minuses. The new ones are basically with respect to this whole definite integral business. So once you add on the extra layer of complexity of having these limits of integration, there's a couple of additional things worth mentioning. So one is that if the limits of integration are the same, like you're going from 1 to 1 or something, that's going to accumulate zero area because it's basically a vertical line. Lines don't have any area to them. So if you don't actually go sideways at all, there's no distance between starting and ending points, you end up with a line which has zero area. So the definite integral is also zero. If you swap the order of the integrals, so if you switch top and bottom, so it goes from B to A and A to B, basically you get the negative of what you would have gotten. And this is sort of a convention that's convenient, but it also matches up with the fundamental theorem of calculus computation. So that's good. And then the subdivision rule says basically, if you want to calculate this entire area, you can break it up into one area and then another area and then add those two areas together when you're done. So if you just stop at some x value that we're calling C, you can go from A to C, find that area, from C to B, find that area, and add the results together. So we won't do one problem that covers all of these things, but we'll try to work a few into a quick example here. The easiest way we can do this is just by not using formulas at all, basically. Just saying, look, say that we know for some function that, if some function f, that the integral from 1 to 3 of this function is equal to 7. And then for some other function from 3 to 1, the integral is equal to 5. So again, we don't have graphs, we don't have formulas, all we have are these kind of blanket statements of this specific area for these two different functions. So then our task is to figure out the value of this kind of combination of them. So again, this is what I would classify as a conceptual question because you're not really computing all that much. We just kind of have to dig into these rules for definite integration. So let's start with the thing we're trying to compute here. And one thing we can do to kind of break this up, and maybe a broad goal, is we know some stuff about just the integral of f and just the integral of g. So if we can somehow get this mess to look like some combination of the integral of g and the integral of f, we'd probably be in good shape. So the first thing we can use is the difference rule, which says, look, you can take the first term and the second term in these inside of here, and then break them up into two separate integrals. So we take g of x, give it its own integral, 2 times f of x, give it its own integral. And just like with, this is sort of the new guy in town here, these limits of integration, but the subtraction piece is just like anti-differentiation, just like the indefinite integral. So the new thing here is that these limits of integration stay the same. They're still from 1 to 3 for both of these integrals, just like the original one was. So then the next thing we could do, this g of x thing is looking pretty good, except that you'll notice it was defined as sort of this funky backwards thing where it goes from 3 to 1, like almost accumulating area from right to left instead of the usual direction. So we can flip that around and say, look, I only know stuff about the integral from 3 to 1 of g of x. So let's flip this from 1 to 3, flip it around using that rule that allows us to exchange the limits of integration, but we're going to get an extra negative sign when we do that. So such is life, we can manage it. Now though, the rest of this is something we can compute. The other thing we'll do, just sort of sneak it in there while we're in the neighborhood, is to take this constant multiple of 2 and use that constant multiple rule to pull it out, and then we get this guy out in front. And now we're actually in a really good spot because this integral is one that we were given a value for. And this integral is one we were given a value for. Here it is. So all we'd have to do is say, oh, look, it's negative 5, because that's the integral here, minus 2 times this integral, which we were told was 7. And if my arithmetic holds, negative 5 minus 14 would take us down to negative 19. So there's an example just illustrating some of those rules when computing stuff with the definite integral. Notice we didn't do power rule or any of that fancy stuff. We were just kind of using these strategies to move toward the integrals that we had some knowledge of, just the integral of f and the integral of g. Okay, so the main learning objective here to talk about is net change. And we get this definition theorem-y thing that really, honestly, isn't any different from the fundamental theorem of calculus stuff we were using. It's really, if you treat Q as F, this is as capital F, this is capital F of B minus capital F of A, which is exactly the fundamental theorem of calculus statement we were using. And this Q prime is just like writing little f inside and then having capital F be the antiderivative. It's just sort of written differently. But the motivation for this is we're supposed to think of this Q prime as an accumulation of some type of area. And more particular to the application, we're supposed to think of it as a rate of change in some kind of formula that we're curious about. So the one we're going to study in our example is Qatari merchandise. So we're going to say this importer has modeled her rate of change in profit since the company was founded. That happened in 1997. This is the rate of change in profit. Notice it's got a little apostrophe there, so you could call this marginal profit if you'd like. This is measured in hundreds of dollars, so we do want to be a little bit careful about units on that piece, but we'll make it work. This is T years after the company opened its doors, so again, T years after the beginning of 97. And then here's the real question. What is the importer's net change in profit? So that's kind of the catchphrase here for what we're looking at. Net change in profit. That's going to be this Q of B minus Q of A situation. And I guess I'm using Q's here because that's what the thing in the definition on the previous slide says. We're obviously working with profit, so this function got named capital P, but we'll make it happen. So this is basically P of B minus P of A. Okay, and then this is between the beginning of the years 2000 and 2003. So we're going to have to turn those into T values, but I have faith we can do that. Okay, so net change, again, just expressing this as an actual profit-y thing. We can write this as a definite integral because this right here is the net change. That's our expression for net change. So we're starting to get some better, not geometric interpretations of what the definite integral is. This is a net change in profit, basically. So we're supposed to take this expression and take it. Oh, this is actually supposed to be P prime. So let's correct that. So we're adding up all the little changes in profit from year 3. Again, this is year 2000 is right there, and the year 2003 corresponds to t equals 6, and that's because 1997 would be t equals 0. So 3 years later would be 2000. 6 years later would be 2003. And then here is us taking antiderivatives. Again, this is P prime that we're taking the antiderivative of. And then all of this expression looks like the formula that we were handed. And here's where what you might term the actual math beginning. But all of this setup is extremely important because without recognizing that this net change thing is something that's a definite integral of this derivative, we would never get to the point where we could use, in this case, power rule to get an answer. So don't discount this earlier stuff. This is definitely still mathematics because these computations can't happen without it. But once we get there, we're looking at power rule through and through. So we're adding 1, dividing by that new exponent. So 0.7 divided by 5 gets us to 0.14. T cubed goes up to t to the 4th, t squared goes to t cubed, t gets up to t squared, and here's this notation again, just saying, look, here's our antiderivative, because that's how we do this definite integral business. Here's our antiderivative. Notice there's no plus c, because we don't actually care. We're not saying that it has to be plus anything. Really, we're sort of implicitly going with the antiderivative that has c equal to 0, because we're just adding nothing. But remember, fundamental theorem of calculus doesn't care which particular antiderivative we pick. So we might as well pick the one that's nicest and tidiest. So the last step is just the arithmetic of plugging in 6's and plugging in 3's. So here is us taking that antiderivative expression, plugging in 6 for all the time, plugging in 3 for all the times, and then what we get is, again, an approximate, but something that's we could have as much decimal accuracy as we might want. Just before we get to the final conclusion, the final countdown here, just as a mention for interpreting this first expression is basically, it's not perfect because we're missing a constant, but this is more or less profit after 2003. And then this is essentially profit up to 2000. I'm just for the record, we're missing a constant because we don't have a particular solution. So I'm going to put basically on here just to kind of save my rear end on this. But so we're saying, look, essentially, if you take the difference in profit from 2003 to 2000, you subtract those, that's the difference, you're going to get how much profit changed between 2000 and 2003, which is exactly the question that we were answering. So we're undoing this derivative, this rate of change in profit, in order to get back to basically profit functions, so that once we take their difference, we can figure out how much has profit changed. So in this context, fundamental theorem of calculus looks really smart. Like it's like, oh, it's just saying if you undo the derivative thing, get rid of this whole derivative business, go back to the original profit functions. Absolutely, if you take the profit in 2003 and you subtract the profit in 2000, you're going to get how much profit changed between those two. So I really like doing some applications with these because it puts that fundamental theorem of calculus in good perspective. So the last consideration here is that the units, so we've got a great number here, but remember the output on profit was in hundreds of dollars. So if we're being super careful about this, we would say this is $100. And so multiplying by 100, we'd have the decimal point go over a couple spots, hence the 1,354 basically. So these are her profits increasing by, not quite $1,500. And again, these are monthly profits, so $1,500 a month between 2000 and 2003. So that concludes 5.3. And we'll come back in 5.4 with some more great applications of the fundamental theorem of calculus. See you then.